right, I guess we'll continue on to our last speaker, who is Rose Yu. She is an associate professor at UC San Diego, Department of Computer Science and Engineering, and her research interests are in machine learning, especially for large-scale spatiotemporal data.
Can you hear me okay?
Yes.
Okay, cool. Thanks a lot for inviting me to speak. So I'm the lead PI of this project called Genie. The goal of the project is trying to develop a generative foundation models for automated climate science. The fact that I work on climate science is also partially due to our previous project funded by Department of Energy, and I was the lead PI of that project in together with 7 other PIs from 3 different universities. The goal of that project is try to discover climate extreme and then trying to extract patterns, then learn deep latent variable models from climate extreme data. So that project is winding down, and we have a sequence of publications through that project. And this DAPA project is a nice follow-up project of that. The new thing that we bring into this project is multimodal. So in this team, we have faculty members from NLP. Taylor Kirkpatrick is an expert in natural language processing and expert from uncertainty quantification. So that's Professor Iyama from data science. And we have our domain expert, which is the Professor Duncan Watson Paris. So he's a climate scientist, also a data scientist as well. And there's me. I work on deep learning, in particularly physics-guided deep learning, trying to ground deep networks with first principles. And this team has a very diverse set of PhD students and master students, and this has just started early this year. So the executive summary of this project is that we want to train foundation models for hypothesis generation in climate science. But of course, we think the development in this project would have implications for other domain science as well, such as molecular science or chemistry and others. Once we have a foundation model, we're going to fine-tune it for a diverse set of tasks. So in climate science, there are some important tasks such as forecasting, which is to project the future evolution of the climate given its path, and causal inference, that is about inferring the underlying causal mechanism or causal graphs from high-dimensional spatial temporal data, and scenario creation, that is to ask what-if questions to help decision makers make better decisions given climate model outputs. And we're also going to look at the classic task in natural language processing, that is question answering. So a key feature of this project is multimodal. And typically in climate science, people only deal with numerical data. So these data include measurements from satellites or simulation output from climate models. However, from the vision of the project, we realized that there's also massive amount of text data that is often appears in textbooks in climate science and also academic journals that we can extract. In addition, there are also climate reports, IPCC report that summarizes the evolution of this field every few years. So how do we combine this rich multimodal data set to design a foundation model is a key question we want to pursue in this project. So we wanted to tackle this goal from several technical perspectives to ensure our scientific foundation model is indeed scientifically consistent. We're going to explore techniques that we are familiar with, such as physics-guided deep learning, Bayesian active learning with uncertainty, and reinforcement learning with word feedback. A notable feature of this project is that we wanted to reduce the burden on our domain experts. So rather than using the typical fine-tuning techniques such as RLHF, we're going to gradually take the domain expert out of the loop, but rather to have automated agents that give us feedback to fine-tune the model incrementally. The potential impact of this project is that we will integrate diverse data and knowledge sources for hypothesis generation. And the goal of this project is to reduce the turnaround time, which is to generate a particular climate scenario given the policy parameter input from the original 6 months to 1 week. Just some background of climate science. So climate models are perhaps the most fundamental tools that scientists use in climate to understand the energy transfer from the land to the ocean to the atmosphere. So there are very complex physical processes that happens in the entire global scale. And typically, climate scientists will look at these climate models that are soup of partial differential equations through different scale of space and time resolution. And in doing that, we discretize this global grid into different smaller grid. And then by looking at the physical processes at different scales, we can understand their interactions and trying to model the future evolution of the system. Now, the major limitation of climate model is the turnaround time. So because of the complexity in these large complex partial differential equation-based models, running a model once usually takes 6 months. So it prevents climate scientists to understand the downstream impact of different climate policies in a real-time fashion. So our goal is to make that faster. And another limitation of existing climate model is that they're very ad hoc. So typically, climate models are designed based on the local parameterization, and then some domain experts specific to a geographical location and the climate phenomenon. So for different global and climate local climate models and the different parameterization, new type of deep learning models have to be designed for every different parameterization. So we thought it would be more efficient if we could have a foundation model that can govern all the different processes and parameterizations and can only need to be fine-tuned for these different parameterizations. We want our model to unlock the potential of public access for climate models, because these days climate models are only limited to climate scientists with rich domain experts to run. So we want our model to be easier to run and faster to run so that they can open up access to the broader community for policy making. So this is the vision of the project. We call it Genie. It stands for Generative Foundation Models for Automated Climate Science. And we have 3 modules in this framework. The first part is the multimodal self-supervised learning. So we will take the numerical data from observations and climate model simulations in numbers, combine that with text data from climate textbooks, academic journals, and the IPCC reports. And after we have trained a multimodal foundation model, we will fine-tune that for different tasks. As explained in before, we're going to look at forecasting, causal inference, scenario creation, question answering, etc. And in terms of fine-tuning this model, we're going to use these physical laws and uncertainty instead of climate experts. So we're looking at grounding these models with physical laws, prediction uncertainty, and in-context learning to ensure the scientific consistency of our foundation models. The example task that we envision is that we can ask forecasting questions. For example, what is the next week's sea surface temperature given the past time series? Then the model will be able to generate the future forecast. On top of that, the model can generate text output as well. So it will give reasons about what is the contributing factors to temperature rise. In this case, it will point out that high sulfur content and SO2 will have a strong effect on the temperature rise. So from my part, I will talk a little bit about this physics-guided deep learning area. So that's the new framework that we have been working on for the past few years. The focus here is that a lot of the existing AI methods are purely deep data-driven. So they learn from statistical patterns, and they don't actually constrain the model to be physically meaningful. So when we apply these tools to scientific applications, the typical limitation of this model is that they don't generate scientifically consistent predictions. And then the models are very difficult to interpret and lack physical reasoning. So because we're dealing with the spatial temporal data that is often governed by physical processes, it is actually crucial to look at the physical underpinning physical laws in this system. So physics has been used to describe the spatial temporal data for many, many decades. And we wanted to bring these tools from physics, such as differential equations and symmetry, into the design and training of deep neural networks. So hence, this hybrid framework combine the best of two worlds together, which I name as physics-guided deep learning. So we recently published a review paper at Proceeding of National Academy of Science. So I put the reference here. I encourage to take a look at this perspective or / review paper where we discussed this framework in detail. The title of this review paper is called Learning Dynamical Systems from Data, Introduction to Physics-Guided Deep Learning. And in this paper, we talked about 4 different type of paradigms to combine physics with learning, starting from more physics all the way to more data. And there is a continuum spectrum of how we can integrate physical inductive biases into data-driven deep learning models. They include residual modeling, trainable operators, equivariant learning, and disentangled representation. Again, I encourage you to take a look at this perspective paper and let me know if you have any feedback. So for this project alone, we wanted to use our previous work for hypothesis generation. So in our ICML 2023 work, we proposed a really new type of generative model to generate physical laws. Instead, in this case, we're generating symmetries from data. So we will want to use our model as a machine for generating different kind of hypotheses. As an example here, we are generating the hypothesis of what is the symmetry group in a particular data set. So here, if you look at the picture, it resembles the overall paradigm of generative adversarial network. However, the key difference here is that in the generator, we're actually not generating fake data, but we're actually generating scientific hypotheses. So for this case, we're generating different type of symmetry groups using Lie algebra generator. And then through the generator, we can generate a sequence of potential hypotheses. And then we have a discriminator that tries to discriminate between the original data and then the data under transformation. So when the discriminator fails to discriminate between these two data sets, then we have successfully figured out the right hypothesis, aka the right symmetry transformation from the data. So from this work, we actually can automatically discover symmetries from large hadron colliders, high energy particle data from large hadron collector. So in this task, we have particles being accelerated close to the speed of light, and we are trying to look at what is the symmetries in this trajectory data of high energy particles. And surprisingly, the model has successfully discovered the Lorentz symmetry group purely from data without any domain knowledge. And then Lorentz symmetry is one of the fundamental symmetries in high energy particle physics. And Einstein used Lorentz symmetry in his general relativity theory. And we use this discovered symmetry to design equivariant neural networks. And it turns out that the prediction performance, so this is classifying different jets right, into B jets, mu jets, and etc. So the classification accuracy of the model our design or using our discovered symmetry has comparable prediction performance as the neural network that is hand designed by physicists. So that is a Lorenz net. And this shows the potential of automatic hypothesis generation using a hybrid method of physics-guided deep learning. Okay, then coming back to fine-tuning part, we wanted to use reinforcement learning from word feedback rather than reinforcement learning from human feedback. So we wanted to ground Genie with the physical domain knowledge. So I mentioned about physics-guided deep learning. And we're going to look at other feedbacks as well, such as uncertainty, in-context learning, and simulator feedback. So in climate simulation, we have these complex models. But running the simulation alone is very slow. So we have worked on emulators that is based on deep neural network. And these emulators can mimic the behavior of complex simulator, but much faster. So we can use the emulator to ground our model with uncertainty. And in this case, we have this set of hypotheses, and we treat them as the blue circle in this diagram. So these are the potential outcomes learnable from data. And then we're going to use our active actor critic network, or the generative adversarial network, to discriminate between the proposed distribution and outcome distribution from data. So this kind of two-player game type of schema will allow us to screen out some of the implausible hypotheses. And we're going to use Bayesian active learning to iteratively fine-tune our model. So rather than generating all the hypotheses in one batch, and that will be very time-consuming, we're going to iteratively query our emulator using Bayesian active learning. So our Bayesian active learning is a kind of a feedback loop that generates hypotheses and then test them against the climate emulator. And then we use a network to discriminate which hypothesis has the highest amount of uncertainty. And then we go back to the emulator and ask for more hypotheses. So we were going to use this key concept called acquisition function, which is the criteria of which we use to determine which hypothesis we're going to query the emulators about. And this latent information gain acquisition function comes from our previous paper. So the key idea behind this acquisition function is that we're going to compute the information gain in the latent space rather than the observational space, because using deep neural network, we can map high-dimensional data into lower-dimensional latent representations. So computing the information gain in the latent space is much more efficient than computing the information gain in the observational space. So as a paradigm, we have, this is a picture from our paper that I showed previously. We have a neural network model that can learn the hypothesis, and then we infer the latent process to figure out the uncertainty. And then we will use this trained model to evaluate the uncertainty of different hypotheses. And then we'll use the acquisition function, which is the latent information gain, to select the hypothesis that is most meaningful to fine-tune our model. And then we iterate this process through a feedback loop. We applied this framework to a different task of learning complex emulator in fluid dynamics. So here we can show that using our latent information gain as an acquisition function, we can significantly reduce the amount of queries required to train the model. So that leads to 68% data reduction. So that's all I want to talk about. And we're continuing working on this framework of Genie, and we welcome feedbacks. Thank you.
Rose, quick question. Great work again. On the symmetry part, how robust is that learning symmetry from data? If noisy data comes in, is it still able to learn symmetries in general? Any sort of things you can share on approximate symmetries and questions of that kind?
Great question. So yes, I think your question actually have two parts, right? Whether we can discover symmetry with noisy data versus whether when the symmetry is not exact. So we actually have papers in both of these top questions. So the first one, so it is in general possible to discover symmetries with noisy data, but of course there is a threshold of signal to noise ratio. So in our ICML paper to appear this year in 2024, we tested the spectrum of a symmetry discovery with noisy data. So it's especially for large symmetry groups, it is actually less robust to noise perturbation. But smaller like symmetry groups, it is quite robust. And then the second question, like when the symmetry is not exact, so we had a paper in 2022 ICML where we proposed one of the first frameworks for approximate symmetry. So in that case, we relaxed the symmetry group with a perturbation, a symmetry breaking term, right? And we can allow the model to learn the symmetry breaking terms from data. So that line of work is still continuing. I hope that answers your question.
Yeah, very much. Yeah, thanks. I found that approximate paper as well.
Great.
Any other questions? All right. Thanks so much, Rose. This was great.
Sure.
Okay, and thanks to Erica for chairing this session. That wraps up today's activities. Tomorrow we'll begin with tutorial 1 at 9 a.m. On climate foundation models from Paris, showing their work on Aurora. Thanks, everyone. See you tomorrow.